Let's now talk about boosting. So boosting is another ensemble approach. When we're talking about bagging, we need to get some kind of unstable algorithms. We want to generate some diversity, but it is relatively passive in the sense that we just feed the model with different training subsets. And we hope that these different training subsets will induce some kind of diversity. So instead, we can make use of boosting. So boosting is basically to actively generate new classifiers from data that are difficult to handle for classifiers. So we tend somehow to, let's maybe see the classic boosting. This is not the algorithms used right now in most cases. This is more an historical algorithm that is interesting to see the idea. So here we have, let's say we are splitting the training set in 3 subsets, x1, x2, x3. So we have these 3 partitions of the given training set. And the point is to train first a classifier on x1. So of course it is trained on a really small subset, 1/3 of the full training set. But anyway, let's use it as h1. And let's train, let's first evaluate x2 data on it. So let's put x2 data on it. And let's get all the misclassified data apart and say, okay, we will use the misclassified data from H1 as half of the training set of our new model. And let's pick up, I would say, a random number of well-classified data. So we just get a 50-50 balanced data set with 50 of the samples that are misclassified by H1 and the other 50 are well-classified by H1 and pick them randomly. And then we will train H2 on this new data set. So the H2 prime, which is basically coming from half of misclassified data from H1 and half of well-classified, will be used to train H2. And so we hope that H2 will be much better than H1 in the cases where H1 is struggling. So then we are evaluating X3 on H1 and with H1. So we are putting data X3 into H1 and H2. So we just kind of evaluate the classification. And when we see a disagreement between H1 and H2, when the two are not saying the same thing, we pick these samples as H3 prime. And then we will train a third classifier on these data where there are some ambiguities. And then from that, the decision will be made by first test a data on H1 and H2. So we get a decision from these two members, these two basic models. And if they disagree, if they don't provide the same decision, we will ask H3 to figure out or to make the final decision, given that H1 and H2 are disagreeing. So this is good to improve performance. It has been shown that to be relatively good, but still, it requires a very large data set because we are splitting the data set in 3 subsets of, I would say, 1/3 of the samples each. So that's kind of small, and that can lead much worse results than training on the full training set. But in the boosting model, when we have enough samples, may give, in fact, increases in performance. You can get this better accuracy with the member approach based on that. But like I said, it is more an historical algorithm. In fact, right now we are, since 25 years, we are relying more on things like AdaBoost. AdaBoost is what we call an adaptive boosting. So it reuses the same data set for basic classifiers. We just use the full training set, but the point is that, so unlike boosting, we are not requiring very large data sets. We can do AdaBoost on regular data sets. And it is able to generate an arbitrarily high number of classifiers. So it's not just limited to say like 3 or 5 classifiers. It can be hundreds of classifiers in some circumstances. So there are many variations of AdaBoost that has been proposed. We'll talk about the M1 variation, so AdaBoost.M1. So in that case, the probability of sampling a data changes according to the errors of the basic classifiers. That means that at first, we just assign an equal sampling weight to every sample. So we have our n samples. We have B1T equal 1/n. So these are the equal weights for every sample, every training set samples at first. Then we are sampling xj from the original training set according to these probabilities. So we have our sample set here, and then we train the classifier HJ on that sampling. So you know that sampling we can pick several times the same sample, like we did with bagging. And then we see that if the error rate of our model is higher than 0.5, it is really bad. It means that our model does worse than random decision, so that's not okay. Well, it's, you know, the epsilon j is stated here. It's can I say it is based on the sampling probability PJT, which is in fact adjusted over time. So we kind of weight everything and use this according to the decision made by our member according to the real labels. And then we are calculating the probability PG plus 1t. So it means that the probability at the next step, at step j plus 1, according to the classification of the training set by HJ. So we have HJ, we apply this on X, and we get some decisions. And based on these decisions, we are adjusting the probability. And this means that, in fact, the hard samples, the samples that are not well classified by HJ, as their probability PG plus 1t increase. And conversely, for correctly classified samples, the probability PG plus 1t should decrease. And we are repeating this L times to get L basic classifiers. So like with some other approaches, boosting and AdaBoost do not require very precise classifiers. In fact, we are looking more for weak learners. So these are algorithms with an error probability that is less than 1/2. So it means that we want something better than random classification. But still, you know, it can be relatively unstable. We don't care that much about stability here. So using a weak learner allows us to get a good diversity in the classification. So, you know, we don't always get the same kind of model or models that are equivalent in terms of functions. We get models that are diverse, that should be different from what we expect. So one simple approach for that is the decision stumps. So the idea of having a really weak learner model to use with AdaBoost, because that's a way to get possibly an ensemble of many models. So this is basically like a decision tree, but it's a stump, you know, it's like a tree that we cut it just after the root. So we have the root that is making a decision. So we have some kind of binary decision from the root, and that's it. With decision stumps, we stop there. So basically we are thresholding according to one variable over one threshold. So the mathematical formulation you see here is that thing. Basically, we have the theta here that is showing us, we have this theta here that is giving us the sign. So it's basically, are we looking for something higher or less than the given threshold? And then we have the variable here. So the gamma here is giving us, we are looking at variable 1, 2, 3 up to D. And then we have the threshold here that is the real value. So we have that threshold over one dimension. It's really just, I would say, aligned with the axis in terms of decision frontiers. And that's it. So how can we determine the right parameters? Simply, we just use that thing. That thing is basically to say for variable j, we are ordering all the samples according to their value. So we get them ordered from the smallest one for dimension j to the biggest one here. And then we are looking at defining thresholds that are alpha. You know, if we just get everything ordered for given variables, we get something like -1, -0.8, -0.55, and so on. We see that maybe between -1 and -0.8, the in-middle decision threshold, really the one that is somehow maximizing the margin, is -0.9. So we say, okay, between -10, -0.8, we get -0.9 as the first threshold here, and so on for the others. Every intervals between two samples, we just cut in the middle with the threshold that is defined, calculated according to this equation here. And then we are building up all the set of all combinations. Let's say, you know, for all the different, let me look, I think it's all the different signs. So basically it's for the theta here. We have 0, +1 or -1. So it is bigger or less than the threshold hues, the threshold itself and the index of the dimensions. So we are looking at all possibilities here. So we have this for variable 1, 2, up to variable d. So we've got all thresholds are signs plus or minus over all dimensions. And then we are looking to get the triplets here, sign, threshold, and the variable that is minimizing the error on the data set here. So we are basically looking at the configuration that get us with the best performance. So this decision stumps, which is a weak learner, is trained that way. And you know, the point is that if we are looking at the weight, you know, we have, so we're just going back here once and twice. You know, we have this probability here, P, well, PG plus 1T. So when we are looking to calculate and or update the probability, you know, we are changing the sampling probability of each sample. And that will affect some of the performance because we'll get with more and more difficult samples that are put in our training set like this one here. So with harder and harder samples in our training set, what we can expect is that over time, we will just get a training set filled up of difficult samples to train on. And then the training error here on the given current weak classifier weighted according to the different probabilities. So basically looking at the higher weights for difficult samples will lead us to something that will be really close to 0.5. So over time, we will get a training set that is so difficult that our decision stumps, for example, or whatever other weak classifier will perform badly. But the ensemble training error itself will go down. In fact, we expect that it will decrease quickly. So whatever the performance of the single classifier, this single classifier is working with many other classifiers. So it is still able better than random guesses. So we can expect that it will provide some improvements to the global ensemble performance. And likewise, we can expect that the ensemble test error will also reduce. Maybe there will be some overfit toward the end where we start to overfit, but in practice, we don't observe that often, or at least if we train just for some limited number of classifiers. If we get, I would say, something different from that, sorry. So we have what we can say, we have overfit not that often with on the just set with AdaBoost. At least we need to go very far away with very difficult cases, difficult long time training. So basically a time of training that is long enough to get us overfitting the training set. So basically the AdaBoost algorithm looks like this. So we have these initial probabilities that are set uniformly at first. Then for each basic classifier that we want to build in our model, we are doing some kind of training. So we are sampling dataset XJ from the original training set according to the probabilities PGT. Then we are training our classifier with dataset. So HJ is trained on XJ. So we train on our dataset that we just get. And then we are computing the error on that dataset. So using the weighted sum over the losses for each sample of our model. So the PGT is kind of weighting much more the difficult samples over time. If the error goes beyond 0.5, we need to stop. We need to say, okay, yeah, this member is worse than random decisions. So we need to stop it here because we will degrade the performance of the ensemble by adding such model to our model. But as far as the error is less than 0.5, we can continue. Otherwise, we stop. And then we calculate our beta j. So the beta j is basically the epsilon j, which is computed on the training set, divided by 1 epsilon j. And this value is really useful for making adjustment to the probabilities and making decisions also, because we will update the new probability pg plus 1t as the following. So basically, we will use an intermediate value, which is qgt here. And this qgt gives us something like, okay, we have this thing here. So qgt here is basically for the one that are well classified. So if the decision is right, we will reduce somehow the probability of sampling that sample by a factor beta. So the beta is less than 1. So basically, we'll reduce the probability of sampling that sample. We will keep the probability the same here for computing the Q, but this step of normalization, where we'll try to renormalize everything, given that we reduce some probabilities here for the well-classified cases, the normalization will increase accordingly the PG plus 1T for the misclassified samples. And in the end, once we are done, we can evaluate the classification of our data as simply the sum, and then we are still using the beta j here, log of 1 over beta j times hj of x. And this for all the members. So this is the decision rule for our AdaBoost model. If we look at how it goes in a given, I would say, example here, we see at first that we are making a decision with estimator 0, that is basically to say, okay, everything that is on the right side here is assigned to the green, and on the left side is assigned to the blue. So it's correct for the blue. No, it's correct. Yeah, all the green are correctly classified here. And only a part of the blue, the one on the left, are correctly classified. We still have, I would say, we have 4 samples, these 2 and these 2, that are misclassified by this first model. But that's fine. And this is a decision stump, that is put simply on the value of x1, whether or not it is higher than or less than -1. Then we go with the second step. So in the second step, what we see, the size of the dot for each sample is increasing according to their probability PJT. So if we are misclassifying one sample, like these 2 here, we would increase their weight accordingly. And then they have more weight. And as such, we will make a new classifier, which is still based on x1, but then it will just make the decision based on the threshold at 1, not -1. So just say that everything on the left is blue, everything on the right is green. So now we have few samples of the green class that are misclassified. In fact, these are the ones here. So we have all these guys that are misclassified in the green at the second step. And so we've got now a third classifier, and this third classifier is basically based on, it is relying on the x2 one. So it's using the other variables. We are thresholding at something slightly below 0, that's 0, and it makes that decision here like that. And it goes such that, everything over this is green, below this is blue, and so on. And so we can see over time the different models that are generated here. So we've got this kind of decisions that goes with different models. So what can I say on that? Well, different steps for the different estimation up to the last time here. Okay, maybe it's not that good here when we see here, but we see, no, it's good, because in fact we need to look at the yellow line. So the yellow line gives us the ensemble decision, while the color is giving us the specific decision at that step. So we see that we are kind of being able to get 100% good classification at step 11. So the model with AdaBoost is able to train and get everything well classified in that case. Might be a case of overfitting, might be not, it depends. But yes, it is able to get it well. In fact, a view of AdaBoost is to say that AdaBoost is working quite well in practice, and it is somehow maximizing the margins for classification. So the point is that learning with higher probabilities, the difficult to classify data, means somehow that these data are kind of in the margin, not necessarily in the margin of geometrical margin like with the SVM. It's more like the decision margins, the voting margin. Somehow when we combine all decisions together, we see that in the ensemble, many of the classifiers, individual classifiers, are not well classifying some of these data. So these are closer to the boundaries in terms of voting. If we look at somehow H prime I as the result of a weighted vote, so this is what I'm saying is that, you know, we can look at this as simply at the votes for class I minus the votes against class I divided by the total number of votes. So this gives us somehow the result for a given HI bar. So with many classifier, we expect that HI bar will lead to 1 for data from class 1 and lead to -1 otherwise, because we are normalizing it. And you know, the point is to say, okay, if for every samples we get wider margins, so now we are kind of able to get in a zone where we don't have much. We have about no decisions where the number of votes is about 50-50. Then we get a better margin, and so we expect to maximize much better on new samples. Even though they can be closer to the margin according to voting, the training will kind of put these margins that will help in terms of generalization. So this is kind of similar to SVM, but not in the same space. SVM is really more about geometrical margins. Here, AdaBoost can be seen as a way to maximize the voting margin. And there are many variants of boosting. You know, one interesting here, given the current discussion, is LP boost, linear programming boosting. So basically, it is learning an alpha. So the alpha is one alpha for each sample. So every every alpha is for one alpha per member basic models that are making our ensemble. And we are optimizing this alpha by linear programming. So basically, we are getting a set of alphas corresponding to each classifier. And at each generation, we are recomputing the alphas for everything. So we are not sticking to the previous values. We are just recompute the new alphas for the full ensemble at every steps in order to achieve the best classification results. And in such model, many parallels can be made with SVMs. You know, it's not the same on some aspects, but it's kind of similar on many others, especially in the way it is trained and so on.